time I just showed that the determinant of the inverse is equal to 1 over the determinant of the original, right? And there's the proof. Um, we also learned that the A is invertible if and only if the determinant is non-zero. That's an important thing to know. So now let us discuss. So let us relate the determinant back to the first idea I gave. So the back to our matrices. So I told you, remember how if you get two vectors, it's the determinant of the vectors is the area of the parallelogram spanned by those vectors. So I mean, obviously the matrices, yeah, a n by one matrix is a vector, but what about if it's like n by n? Like, what does this mean? Well, this is what it means. So if let's just take for example A equals A, B, C, and D, then the vectors A1, which is the first column of A, and A2, uh, A2 are what makes the parallelogram, okay? So this is what the vectors are for the matrix. So let's just state a result, and we'll finish up this little thing here. So let A be n by n matrix with 0 entries, then the volume of the parallelepiped. So pipette meaning this parallelogram is in 2 dimensions, a parallelepiped, and then area other than we call them this, right? So generated by the columns of A is the determinant of A, and just like its absolute value, right? Because remember, it can have a minus sign, but it's just orientation. It just means it has an orientation. Okay, so last thing, the very last thing I just want to give out is one more theorem, and then I'm going to give a challenge problem. So this challenge problem should be fairly easy, hopefully. Based on all the results you've done already, it should be very, I guess not trivial, but it shouldn't cause too much headache. So theorem 3.36. So let A be an n by n matrix, then we know that the determinant of A is also equal to the determinant of A transpose. Yes, yeah, I can go back. Here in a second. Okay, so basically, it doesn't matter if you transpose the matrix, the determinant stays the same. I mean, you can make the argument using the operations we've already done. Well, actually, no, that's a lie. It's actually more complicated than that. You would have to. So, okay, so if I take the determinant, uh, actually, no, it's not that bad. Yeah, the proof isn't too bad, but regardless, you shouldn't be worried about the proof. This is the one you should, I guess, think about. Problem. So, let's A be a skew, symmetric well, matrix proof that if n is odd, so meaning the dimension of the matrix is odd, like it has is a 3 by 3, 5 by 5, anything odd, that's odd numbered, then the determinant of A must be 0. Okay. So this one, if you can really so everything we've talked about, you should be able to use that on here. Like anything, all the challenge rounds I give aren't stuff that I isn't that I give and you guys not being able to solve. These are all problems that you'd be able to solve with all the resulting theorems we've done of. So all right, so okay, so that finishes the section. Now we're going to go over the next section, which I think is a ridiculous title because there's really no point in this one, really. So section 3.4, but I have to go over it anyway. So this one is applications of determinants. Now you might ask why I said it's ridiculous, because really there's no applications to determinants other than like quantum field theory and even there, like it's like you just use it as theory. So the stuff we're gonna go over right now, you'll never see people use in practice, but it's on the syllabus, so we have to go over it. So we will now see, I guess, where determinants are, I guess, useful, not in real life, but in math. Sorry. But you should probably maybe just know it's because a lot of the stuff here, while it isn't used practically, it is used for theory. Like determinants are useful in theory. They're not useful for practical purposes of like implementing in a computer or like trying to solve like systems of equations or anything like that. Even though one thing we'll see here is exactly that. We will now see where determinants are useful in math. So I'll only give you the things I think are useful. Anything else that's in the section, I don't think are useful. So, question: is there a explicit formula to find the inverse of a matrix? And the answer is yes. And how can we do this? Well, first let's take let's define something new here. So we're going to define something called the adjoint of a matrix, which again, this is a very standard thing to know. So definition. So let A be an n by n matrix, and Cij be the ij cofactor of A. So remember the cofactors, you take the sign and then multiply it by the minor, right? That's what the cofactor is. So now the matrix of cofactors is this. You literally get the cofactors and you plug them into a matrix like this. Okay, so this is called the matrix of cofactors. So get all the cofactors. Remember how we use them? We never we just added we used them to find determinant, right? We added them together and then got a number at the end. But instead, now we just take those numbers and just plug them into a matrix, and that's what we call the cofactor, the matrix of cofactors. Now, the transpose of this matrix is called the adjoint of A and is denoted as ADJ of A. Okay, so ADJ of A is just going to be the transpose of that guy up there. So it's going to look like C11 all the way to C1N, N1, Cn, like this. Okay, so this is the adjoint of the matrix. So again, so I was telling you this stuff isn't useful practically, but for theory it is useful, and we'll see right now how that can be useful. So so remember how I gave you the formula for the inverse of a 2 by 2? Remember it was like 1 over, well, the determinant of A times like that matrix thing. Well, we can use this to actually show that formula is true. So but first let's just do an example. Let's do this example. 3.41. So find the adjoint of, let's say, A equal -1, 3, 0, -2, right? The solution. So we need to find the cofactors. So let's find C11, okay? So let's take this matrix and find the cofactor for C11. So we need to find a minor. So it's this, take away all that stuff. So it's going to be equal to -1 squared of M11, which is M11 is just going to be the determinant of -2. So if you take a 1-by-1 matrix and find its determinant, it's just whatever's inside, okay? So this thing will be precise. So it's just going to be M11, which is the determinant of -2, which is just going to be -2. Now, this doesn't mean absolute value of negative. This is more like determinant of the matrix. So I think it's better if I put this notation. So the determinant of the matrix -2, which is -2. Okay. So okay, so let's do the same thing for C12. So this be -1 to the third of M12. So let's do the same thing, get the minor for 2. So cross that out. So it's just going to be the determinant of negative determinant of the matrix of 0, which is just 0, right? Do the same thing for the other one. C21, -1 to the third of M21. So same thing, right? You take wait, yeah. So this one, so it'd be -1 determinant of the matrix 3, which is just 3. And then, oh, sorry. So you can already see that this is like this is like completely tedious, right? And this is just a 2 by 2. So this is why I say it's not practical, because it's, I mean, imagine trying to tell a computer to do this for like a million by a million system. 2 2 that'd be determinant. So just take away, I don't know, so it would be this one, the matrix -1, which is -1. All right, now we have our all our, yeah. Sorry. Oh yeah, -3. You're right. Yeah. Yeah, -3. Yeah, yeah, perfect. Why is it to the power of 2? Which one? Oh yeah, sorry, it's to the power of 4. Sorry. Yeah, there you go. So yeah, but it's still the same thing. It's just going to be -1. All right. So now we plug them into our matrix, right? It's so you can say, so you do C11, which is -2, C12, which is 0, C21, -3, C22, which is -1. Take transpose. So the adjoint of A is equal to -2, 0, -3, -1. Yeah. Yes. It's just called the matrix of cofactors. Yeah. Which one? One, 4 was 1, 2, 3, 4 was -1. No, it should be negative, and it should just be 1. Sorry, -1, right? There's a negative here, so that's. Uh, is this what you're talking about? So yeah, so it should be so this becomes 1, so it's just going to be 1 times the determinant of -1, which is just -1, right? So yeah. Let's see. I think I pretty much got that. Yeah. Okay. Okay, so as you can see, this is very, imagine if this was a 3 by 3, you would have to do 9 of these, right? So not very practical, but useful in theory. And we'll see the usefulness right now. So now we can derive a formula, so-and-so, for the inverse of any matrix now. So 3.41. So if A is invertible, then A inverse is given by 1 over the determinant of A times the adjoint of A. Okay. So you can prove this by, so you would have to take the cofactor and then, yeah, no, it's actually not that obvious to do. So you would have to do induction. Yeah, you probably have to do an induction proof. And then, yeah, never mind. Forget about that. But yeah, so that you can actually derive the result from a proof, and this is a very nice little compact formula that we can get for the inverse of a matrix. But again, we know already like ways to find inverses of matrices, right? Obviously, computing the adjoint is going to be far more bothersome if you were just to do the augmented trick I did. Remember, you take the matrix, put the identity, RREF it, you get the inverse like that. But this is where we can get something nice. So example 3.42. So let's show that if A is equal to, let's say, A, B, C, and D, and AD minus CB is not 0, then A inverse is equal to 1 over AD minus CB times DA minus C minus B. So this is the formula I gave you, remember, as a result. So now let's actually use the adjoint thing and show that this is true. So how do I say? Oh yes, solution. So again, finding adjoint of A, we get this. So again, so we're going to get C11, which is going to equal to negative 1 squared times the determinant of D, right? If we just do the minor stuff, which is going to equal D. 2, C12 is going to equal negative 1 cubed determinant of C. So this is going to be negative C. C21, negative 1 cubed determinant of B, which is just going to give me minus B. And C22 is going to be equal to negative 1 to the 4th determinant of A, yeah, which is just going to be A, right? So we got the cofactors. Size, oh, come on. So now we can do, so the matrix of cofactors is going to be D minus C minus B, A. Take the transpose of this, which will give me D minus C minus B, A. So this thing is the adjoint of A now, right? So, and the determinant of A is equal to A times D minus C times B, right? And we know that this is not 0 by our assumption. So then by theorem 3.4.1, we know that, well, you just plug it in, right? Then you just get the, then you'll just get A negative 1 equals 1 over AD minus CB times D minus B minus C times A. So this is how you can show that the inverse is given by this. Okay, so let's just do one more, I guess, theoretical tool. Yeah, I can go back. One more theoretical tool, and we can, I guess, call it, well, I'll answer here in a second. So the last thing we can do that I think is useful is something called Kramer's rule. It's more, again, it's not, you don't use it ever to do whatever, for what it was meant for, but it is still useful. All right, so I'm going to go back over here. So now let us shift. So now let us shift our focus solving systems again of linear equations, okay? We can use, so basically, and we can solve a system of linear equations only if it has a unique solution in terms of its in terms of the determinant of its coefficient matrix. So, and that thing is called use Kramer's rule. Okay, and this next theorem is Kramer's rule. If a system of n variables and n equations has a coefficient matrix A with determinant of A is not equal to 0, then the solution to the system is this thing. So x1 would equal the determinant of something called a1, which I'll mention right now what it means, over the determinant of a, and you keep doing this for all the variables, determinant of an over the determinant of a, where the ith column is the column is the column of constants in the system. And what I mean by that is, if your system, you have your variables over here, right, with its coefficients, and then you have your equals to like 2, right? So that side, on the right side of the equation, those are the constants that they're talking about in this theorem. Okay, so we'll do one example for like one solution because it becomes a oh, okay, yeah. Can you see the bottom? You can't. Okay, here. So we'll do one example, and then basically I'll just, I guess, announce something right now in a second. So so let's do our last example of this section. 3.4.3. So let's solve for x only. I'm not going to do every single one. So that's a 2x. So plus 4z is equal to 2. So yeah, so this thing right here is a 2x. Okay, so let's solve for x in this equation, okay? So using Kramer's rule. So this is how it does, how you do it. So basically what you do is you identify your coefficient matrix A. So here, A is equal to -1, 2, -3, 2, 0, 1, 3, -4, 4, okay? What is your A1? Okay, well, for A1, what you do is take the first column of this and replace it with a column made out of these guys, okay? So that will be the A1. So for example, A2, you take the second column of A and replace it by those constants there, and so on and so forth. That's what the A1, AN mean. Okay. So for us, since we're solving for x, we need A1. We have A1 is equal to, well, it's going to equal 1, 0, 2, which is this stuff right here. And then just leave the other stuff the same. Okay. And then find the determinant of each one of those. So I won't do all the computations. You guys know that. So the determinant of A should be 10, and the determinant of A1 should be equal to 8, right? So now all you do is use Kramer's rule. So take determinant of A1 divided by determinant of A, and that should be your solution to x. So remember, when we set this up, our variables are x, y, and z, right? So if I wanted to solve for z, I would use A3 instead of A1. If I wanted to solve for y, I would use A2, okay? So on and so forth. So x is going to equal to determinant of A1 divided by determinant of A, which is just equal to 8 over 10 or 4 over 5. Okay, so basically, so I didn't realize, I don't know, did you guys, by the way, okay, let me ask you this. Do you feel like my pace was a little fast with the material a little bit? Okay, so, yes, okay, so basically then, okay, all the time. Okay, so basically this ends the material for exam 1. So what we can do now, since we have about 2 weeks, is review practice problems in all the sections. Uh, uh, it's that way, since I was going, I guess, fast, I didn't realize I was going that fast. We can at least go back and hit all the points again for chapter 1. What is it? Yeah, chapter 1, 2, and 3. Okay. Yeah, so we'll basically focus or now shift our focus off on practicing actual problems. So we'll do. I guess I can label. I can label them. I'll label them from easy to medium to hard, and we'll do just a bunch of them. Yeah, I didn't realize that I was going too fast. I thought, whenever you teach math, in your head it all makes sense, and in your head you don't think you're going fast. But I do realize, I was a student, and I do realize, like, if I'm like paying attention, they can be going fast because in their mind is like, oh yeah, this is easy. So we'll go back and hit all the points again. Yeah. So I have to focus on. So this weekend I'll focus on basically gathering all the problems, and then I'll send you all the problems hopefully by the weekend or so. And then next week we'll just hit the problems running. So we have all of next week and then all of the week after, right? So let me see. Where is it? So we have all of this week, then all of this week. So that's 2 weeks of practice. So 1, 2, 3, 4, 5, 6, 6 class periods of review basically. Okay, perfect. Then we will do that. Are we what? So are we done with today's lecture? I think we are. The test is March 1st, yes. Okay, so what was I thinking? Yeah, I guess, okay, so I guess since we finished a little earlier, I guess I'll send them for sure. Yeah, we finished lecture. Um, I guess what I can tell you is basically, where does determinants come up? Well, it comes up in 2 areas I can think of. And they're not areas that I can just like explain. What time is the exam? I'm thinking I might make it all day, but within a specific time limit. So you can take it any time, but once you take it, there'll be like a timer, like maybe 2 or 3 hours. So I think I'll make it this way. So at least that way people don't have to like be there at 11 or whatever time it is right now. They can just take it during that time.
Okay. So I have another exam that day.
Uh-huh.
That's solid. So would you be able to like make some exceptions, do it like Tuesday
What, Tuesday what?
for the I mean, I'll just email you about it.
Okay, okay. Yeah. Can we send in our work for the partial credit? And you mean like the latex stuff, or are you talking about the challenge problems? Oh yeah, so that will be on grade scope. So I'll email details about that. So you'll turn in your. No, no, you can leave. There's nothing else left. It's just gonna be like probably like logistics of like the exam stuff. But yeah, so the exam is gonna be, you're gonna turn the exam on something called grade scope. I'll give you instructions on how to sign up for that. Again, that's a free software. Um, and I'll basically give you either a PDF of the exam, or I'll put the exam on there. And then basically, if I give you the PDF of the exam, you do your work on on paper, label your work like this is number one, number two, number three. Uh, can we do it on an iPad? I mean, yeah, like as in like this, like if you can like do it and then like turn this stuff in. Yeah, you can do that. Yeah, that's fine. I mean, it's not like being it's, I'm not under the impression that you guys won't have access to the internet or something like that. But yeah, I think that'd be fine. Plus the exam, so I'm gonna make the exam to something where it's fair, it's not hard, and it will cover a lot of the review stuff that we did. But you can't just go on the Google and just Google it. So I will make it to where it's at least there's a reasonable trade-off. Um, it's fair to where it'll cover the material that we do for the next 2 weeks, but it'll be I'll try to make it ungoogleable or in a sense, right? But yeah, so let me upload this stuff. But yeah, I mean, yeah, you guys can go now if you want. Uh-huh. Which ones? I will decide that as I